Today, I will be presenting my work end-to-end semi-supervised learning for video action detection. This work is done in collaboration with Professor Rawat at CRCV Lab, University of Central Florida. Video action detection can be divided into two subtasks. First is action classification, which means generating a class label for the video. The another one is spatiotemporal localization, which means generating per frame annotations. Since both of these are required to train the model, we need huge data sets to train video action detection models. Thus, we propose another method which uses the unlabeled data efficiently. In our work, we used a semi-supervised approach. Semi-supervised learning has two subsets. One is a label subset, where we have both the ground truth annotations as well as the class label. The another one is the unlabeled subset, where we don't have any information about the class as well as the ground truth annotations. Generally, the unlabeled subset is bigger than the label subset. Now, coming to the related work, there has been existing works on image classification and object detection domain. From the point of consistency regularization, pseudo-label approach, and generative, we particularly focus on consistency regularization approaches. Extending image classification approaches to object detection, we not only classify the object, we also annotate the object in the frame. So now the question is, can it be extended to videos? For the classification consistency, we can just replace the 2D network with a 3D network and then get the features and apply consistency on them. For the spatiotemporal consistency, we can extend object detection approaches. But the question is, does it really cover that temporal aspect? No, because it just spatially compare the pixel-wise location between the frames. Therefore, we argue that we can exploit the temporal continuity of the video and propose two approaches, temporal coherence and gradient smoothness. Temporal coherence means taking the relative displacement of the foreground pixel in the temporal dimension over a finite amount of frames. We compute the variance of the pixel in the current frame by measuring the relative shift in its position in future and past frames. We generate a variance map for the whole video. The variance map of a video attend to short-term fine-grained changes, concentrating on the continuity of the predictions. Now, coming to the gradient smoothness, the first-order gradient of a spatiotemporal region along a temporal dimension provides a gradient flow map. Since the offset is small in temporal dimension, the first-order gradient map should be smooth. Taking the second-order gradient signifies the change in this first-order gradient. As the offset is small, the second-order gradient should be 0. The spikes in this map determine the change in the continuity of the temporal gradient flow map. We utilize this map as an attention to enforce the long-term smoothness of spatiotemporal localization. Now, here is the brief summary of our proposed approach. We get a video, pass it through the augmenter, generate two views. We calculate the supervised loss and an unsupervised loss. In our case, it's consistency loss. Now, walking through each module in depth. Firstly, we pick a video from a label or an unlabeled set. We pass it through an augmenter to get the augmented view. Then we pass it through the model to get the predicted localization map, and we generate variance and gradient maps from them. Combining them all together, we calculate the supervised loss for the label set, and then we calculate the unsupervised loss for the whole batch. We add attention to the spatiotemporal localization consistency using gradient or variance map. Now, coming to the results, we vary the different percentage of labeled and unlabeled set. Here we can see at 15%, our approach is comparable to 100% supervised results for both Fmap and Vmap. Now, comparing it with other semi-supervised approaches, we have two approaches from images, which is mix match and pseudo label, and the third one is from the object detection approach, which is co-SST. We can see that our approach outperforms all of them. Visually comparing them with the other semi-supervised approaches, we took a challenging case where a person is diving and the actor is small and is moving fast. We can see at the bottom row, our approach accurately defines the localization of the person. Now, to summarize, this is the first work on semi-supervised action detection. We propose two novel temporal continuity constants, a temporal coherence and gradient smoothness. Now, 20% of the annotations outperforms fully supervised approach. Thank you.